Dear students, now we are going to derive the expression for moment of inertia of a solid cylinder. The first case is about finding out the moment of inertia about its own axis of symmetry. Okay, so for this we will simply be considering a solid cylinder like this. Okay, and the solid cylinder is of length small l. Okay, say this length is small l, and this is a its own axis of symmetry. Okay, and the radius of that particular cylinder is capital R. Okay, now we are going to consider a small elementary part of this cylinder, bigger cylinder. We are going to consider a coaxial cylinder. Okay, so inside the main cylinder, so we will be considering like this, a coaxial cylinder. Okay, and this coaxial cylinder is interestingly is like this. Okay, so you need to imagine in 3 dimension. Okay, so it's like this. Okay, and this goes like this, and suppose that, let me change this color. Okay, suppose that this much is x, this much is dx. Okay, and let us consider this to be x, this to be x dash. Okay, x dash or x prime, whatever I call. And then yes, so if now let us, what is a volume? Okay, volume of the solid cylinder. So you know that the whole this particular, if you have a solid cylinder like this, okay, and this area is actually pi r square if its radius is small, capital R, and its length is small l, so volume is basically given by pi r square small l. Okay, so and since mass of this particular cylinder is capital M, so if I ask you what is the mass per unit volume of the solid cylinder is equal to m by pi r square n. Okay. Now let us talk about this coaxial cylinder. Okay, so this coaxial cylinder is basically lying in this region. So this region, this coaxial cylinder is here. So this is lying in this region. This is a coaxial cylinder. So you can imagine that inside the main cylinder there is another cylinder like this. And this is not a solid cylinder again, it is a hollow cylinder. And this hollow cylinder is like this. Okay, so this is of thickness dx and radius is x. Okay, now if I ask you that what is the mass of that particular now let us consider now what is the now volume of the coaxial cylinder of radius small x and thickness dx is equal to, so it is again 2 pi x, because the circumference that will be coming out, so it is not a circle, actually it is a ring, so its circumference is x and thickness is dx, so 2 pi x dx, but it is of length again n. So this is a volume of the coaxial cylinder. Therefore mass of the coaxial cylinder is equal to 2 pi x dx into L and m by pi r square into L. Okay. So here also you can see that the L and L gets cancelled. Pi gets cancelled. So it is again 2m by r square x dx. Okay. So similarly, moment of inertia of the cylinder about the axis of symmetry x prime is equal to, so you know that already we have discussed in previous video that moment of inertia is nothing but mass into distance square. Distance is means the distance of that particular element from the axis of rotation. So mass already we have obtained this much, so 2m by r square x dx, and we have distance square x square. So now we have 2m by r square x cube dx. Okay, so therefore total moment of inertia of the solid cylinder is I equal to, so we have got the moment of inertia of this particular thing. Okay, it is a coaxial cylinder. So to get the full cylinder we need to add so many coaxial cylinders like this, and only we can get the full cylinder. So obviously we need to integrate the moment of inertia of this coaxial cylinder from for the different limits of x to get the total moment of inertia. So it will be like 2m by r square x cube dx. Okay, so x is what here? X is nothing but the distance. This is the x, so this is nothing but distance of that element from the axis. So the minimum value of x comes here, maximum value of x comes here. So minimum value of x here is 0 on the axis, and this is the maximum value of x on the surface of the cylinder or rim of the cylinder, so that is r. So again, as in the previous case we have done, it goes from 0 to so this 2 gets cancelled, so this gets cancelled, so we have half mr square. So you can see that the moment of inertia of the cylinder about its axis of axis of symmetry is similar to that of the circular disc. Okay, so similarly we can also find out the moment of inertia of this solid cylinder about an axis passing through its center and perpendicular to the axis of symmetry. Okay, so for that we need to take the help of different theorems for moment of inertia. So let us consider the case B for that. So what is the case B? So here case B is to find out the moment of inertia about an axis passing through its center and perpendicular to its own axis of symmetry. So for this, now let us draw a diagram, as we have already drawn the diagram of a, sorry. Okay, suppose let us consider a similar cylinder like this, as we have already considered, of mass capital M and radius of mass capital M and radius capital R. Now we need to find out the moment of inertia about an axis passing through its center, and say let this be y dash, and let this be x dash. Okay, now if I ask you that, so we are considering that x dash be the axis of symmetry and y dash be the axis perpendicular to x dash. Okay, so now we need to find out the moment of inertia about this axis. Okay, so for this what we are going to do, so as usual we will be considering a small element here. Okay, so that how to consider a small element, so we will be considering a small element here like this. Okay, and this small element is again of consider that it is of distance, it is at a distance uh, x. Okay, and it is of thickness. Okay, it is of thickness like this, and this thickness is dx. All right, and this is the center O, and this is the radius capital R. Okay, so we have considered a small element or a small circular disc or at a distance x from the axis y dash, and we have also considered that it is of thickness dx. Now mass per unit length of the cylinder is equal to, you know that total mass is small m, sorry, capital M, and it has a total length of small l, so it is mass per unit length will be m by l. So it's very much clear. Now you know that this particular shaded area, that disk that we have considered like this, the distance of the disk, what is the length of this disk? This length is nothing but dx. Okay, so if I ask you what is the mass of this particular small element or small disk of thickness dx, then it will be, therefore mass of the small element of the cylinder of thickness dx is equal to capital M by small l, and then we have dx. Okay, now moment of inertia of this particular disk, this element of the disk, about the diameter of the rod. Okay, about the diameter of the rod will be, so therefore moment of inertia of the small element of thickness dx about the diameter of the rod is equal to, so as we have already discussed in a previous case, the moment of inertia of a disk about the diameter, about the diameter means about the diameter of the disk will be like this. Or about diameter of the rod, diameter of the rod is nothing but this one. Okay, so that is nothing but m r square by 4. So here what is m? It is m by small l into dx. Okay, and r square by 4. Okay, so therefore moment of inertia, moment of inertia of the disk about y y dash axis is equal to. So if I ask you what is the moment of inertia of this particular elementary disk about y dash, so then we need to take the help of parallel axis theorem. So parallel axis theorem says that the moment of inertia of this disk about this axis will be equal to sum of moment of inertia of the disk about its diameter, that means this thing, and multiplication or product of mass into distance. What is the distance between this? So this is the distance is x. So we have from parallel axis theorem, first of all, moment of inertia of the disk about the diameter, okay, about the diameter itself. So let me remove some of the unnecessary parts. Okay. Yes, now it's better. So parallel axis theorem says that the moment of inertia of this particular disk, okay, of this particular disk of a certain thickness about this axis y dash is equal to moment of inertia of the disk about the diameter and product of the mass of the disk and the distance between this two parallel axes. So it is x. So first of all, it is m by l dx r to the power of r square by 4 plus again m by l dx. This is the mass of that particular disk, and it is equal into x square, multiplication of the product of the mass and the square of the distance between the two parallel axes. Okay, so here the parallel axes are, this is the one parallel axis and this is the another parallel axis, the diameter. So we can simplify it. So it will be like m r square by l 4l, and it will dx, and it will be m by l, and it will be x square dx. Okay, so therefore moment of inertia of the cylinder about y dash is equal to is I equal to, so moment of inertia of the cylinder about y dash. So you know that if I keep on adding this kind of cylinders, many disk, then it will give the total cylinder. So whatever integration moment of inertia we have got for this particular disk of thickness dx, we need to integrate this to get it for the whole of the cylinder. So that means we have integration m r square by 4l dx plus integration m by l x square dx. So here x goes from, so x is a distance from the center. Okay, x is the distance of the disk for the center. So that distance, this disk will, if you consider symmetry of this particular cylinder, then once it will go from here to here, and then it will go from here to here also. So if you consider this to be 0, this will be l by 2 and this will be l by 2. So you can say that the value of x can go from here to here. So it goes from minus l by 2 to plus l by 2. So it will be minus l by 2, L by 2, and it is also minus l by 2, and this is also plus l by 2. So we already have mr square by 4l, and it is dx, okay, integration minus l by 2, and it is plus l by 2, plus we have m by l, so it is x cube by 3. So already we have this, so minus l by 2, and it is plus l by 2. So here we have mr square by 4l. So it is L by 2 minus L by 2 plus m by L. So it will be L cube by, so 3 we can take it out. So it will be L cube by 8 minus L cube by 8. So finally it will give mr square by 4l, and it is twice L by 2. Okay, and then it will be m by 3l. Okay, and it will be 2 L cube by 8. Alright, so 2 4s goes 2 2 goes, so it will be m r square, L gets cancelled, mr square by 4, and then we have 3 and 4 multiplied, so it will 12. Okay, so it is m by L, and this L gets cancelled, so ml square by 12. So it's simplified manner, it looks m, and inside that it will be r square by 4 plus L square by 12. So this is the moment of inertia of the cylinder about an axis passing through its center and perpendicular to the this axis of symmetry. So if you have a very thin rod, if the rod is very thin, so capital R is approximately 0, is very small, so I will be equal to m L square by 12. So that's all for the moment of inertia of a solid cylinder about the axis, in two cases, about the axis of symmetry, and also about an axis passing through its center and perpendicular to its axis of symmetry.